Hi everyone, my name is Priya DOMINIC and I am a second year PhD student at Laboratoire Hubert, Curien, and today we will discuss my work on the insignificant role of oxidation on ultrafast high-spatial frequency ellipse formation on tungsten. So the objective of this presentation is to give you a short introduction on laser-induced periodic nanostructures and to explain the formation mechanism based on oxidation, which ultimately leads to the question, is there any significance of oxidation for the formation of lips? And then I will explain about the experimental setup used for this topic. And then I will proceed to discuss about the results to analyze the morphology of nanostructures used by using SEM, AFM, and TEM characterization techniques, and we will discuss about the influence of pressure on HSFL formation, and I will finally present the main conclusions of this work. So in order to give you a short introduction on the laser-induced periodic surface structures, so they are nanoripples or nanostructures that are formed on a material when a laser is irradiated on the surface, and they are categorized into two. So we have low spatial frequency lips or LSFLs, which have a period approximately equal to the wavelength of the laser used. And then we have high spatial frequency lips or HSFLs, which have a period very less than the wavelength of the laser used. And in figure A and figure B, you can see the topography of these kind of LSFLs and HSFLs formed on a titanium alloy. And you can see how their periods are different, and also their orientation is also different for both LSFLs and HSFLs. And proceeding to discuss about the applications. So they have a wide variety of applications in different fields, and they can be used for wettability modifications or for producing structural colors, or even they have a lot of applications in biomedical fields and so on. So it is important to understand about the formation mechanism of this kind of structures. Until date, there are a lot of models that tries to explain the formation, and the two main models are the electromagnetic model, which says that they are formed due to the interference of the incoming laser beam with the scattered beam, and then we have the matter reorganization models, which says that they are formed due to the self-organization of the molten material, which is formed by the laser radiation. And recently, there is another model that that explains the formation of the nanostructures based on oxidation. So in figure 1, you can see a titanium film, and according to this explanation, it says that at points where the threshold intensity is exceeded, titanium reacts with oxygen from the atmosphere, forming titanium dioxide. And as the titanium dioxide growth increases on the surface, the oxygen penetration into the oxide layer through the oxide layer decreases, and eventually halting the process. So according to this explanation, it says that the formation of oxide on the surface of the ripples somehow provides a negative feedback to the overall growth of the ripples, and thereby stops the ripples formation and thereby controls the ripple formation. And in figure 2, you can see the main results of a numerical simulation on chromium nitrate that says that you need at least 100 nanometer thickness of oxide layer for the formation of certain nanostructures. So all these studies and observations make us wonder about the extent of significance or extent of influence of oxidation on the formation of nanostructures. And it is very important, and thus it is very important to have an experimental design that addresses this topic of influence of oxidation on the formation of nanoripples. And when we talk about oxidation, the oxygen can be incorporated to the metallic surface from two sources. So it can either come from the atmospheric oxygen, or it could also come from the native oxide layer, that is the adsorbed oxygen layer of few nanometers of thickness that is present on the metallic surfaces. So in order to address and in order to address all of this, and in keeping in mind all of these points, we have designed the following experiment. And in figure 1, you can see the basic experimental setup, which consists of a vacuum chamber, and we have a tungsten, well-polished tungsten surface, and we are focusing a titanium sapphire laser of 800 nanometer wavelength, 1 kilohertz repetition rate, and 60 femtosecond pulse duration for the production of high spatial frequency lips or HSFLs. And so in order to study about the influence of oxygen or different gaseous environments on the formation of ripples or HSFLs, we are doing this experiment for different 5 different gaseous conditions. So the first one is we are doing the experiment for ambient normal atmospheric surroundings, and then air 10 millibar, then nitrogen 10 millibar, argon 10 millibar, and vacuum 10 raised to minus 7 millibar. So very high vacuum. And so when we are doing this experiment under vacuum condition, it actually ensures the elimination of oxygen incorporated from the ambient. But we still have the topic of native oxide layer to address, or we still have to eliminate the role of native oxide layer. And this can be achieved by using a technique called sputtering. So in figure 2, you can see how this is done. So we have the vacuum chamber, and we fill the vacuum chamber with an argon gas, and then we provide a DC power supply, and it creates argon ions which sputters off the tungsten native oxide layer from the tungsten surface, and hence will give a native oxide layer free surface, and thereby elimination of oxygen incorporated from native oxide layer and ambient is possible. So all this experiment, that is with sputtering and without sputtering, and all the radiations under all the different gaseous conditions are done for the same laser parameters. So we use effluence of 0.35 joule per centimeter square and 25 number of pulses for all the laser irradiations. And we have 2 sections of experiment. So first section is without sputtering under 5 different gaseous conditions, and the second section is with sputtering under 5 different gaseous conditions. And chances of any interaction with oxygen from the ambient or from the native oxide layer is very negligible in this setup. And so going through the results, first we see the same images of HSFL formed without sputtering. So we have beautiful HSFL structures, as you can see from the figure, of very small period, which is parallel to the polarization direction of the laser for ambient condition: air 10 millibar, nitrogen 10 millibar, argon 10 millibar, and vacuum 10 millibar. And the formation of these structures under different gaseous conditions, even in the absence of any air, that is under vacuum, indicates the insignificance of ambient air for the formation of this kind of structures. And then we have some images of HSFLs formed with sputtering, so without any native oxide layer. And here also we can see HSFLs with very small periods for all the different gaseous conditions formed, and it indicates the insignificance of any native oxide layer for the formation of ripples. So we have the same images for with and without sputtering, which indicates the insignificance of ambient air and native oxide layer for the formation of HSFLs. And in order to get an idea about the height or the amplitude of the HSFLs, we did some atomic force microscopy images, and the height profile corresponding to different gaseous conditions for without sputtering and with sputtering indicates HSFLs of very small amplitude. So we have sub 20 nanometer amplitude of HSFLs formed for different gaseous conditions: for ambient, for air 10 millibar, for nitrogen 10 millibar, for argon 10 millibar, and for vacuum. So, and in order to ensure the height profile that we got from AFM, we did some cross-sectional image using transmission electron microscopy. So extraction of lamella for TEM analysis. So in figure A, you have a laser spot, and we extracted the lamella from the center of the laser spot where there are structures. And figure C is the image of the lamella extracted. So the lamella is very thin section of the material of less than 100 nanometers thickness, and in region D you can see the HSFL profile, HSFL cross-sectional profile image occurred by TEM. So here you can see the inverted image of the HSFL. So here is the tungsten, and this is the relief and valleys corresponding to the HSFL. And then figure E is a very enhanced image of the relief of the HSFL, and the scales on the figure indicate that indeed the amplitude of the HSFLs obtained are sub 20 nanometer, which agrees with the AFM analysis. So ultimately the morphology of the HSFLs is like has sub 100 nanometer periodicity and sub 20 nanometer height profile. For almost all the HSFLs that we obtained has the same approximately same morphological characteristics. And so the influence of pressure on the period of HSFS. So to study the influence of pressure on the period of HSFS, we plotted a graph of period or amplitude versus the processing conditions of pressure. And when we compared the amplitude for different pressure, the amplitude varied very randomly for different pressure conditions. And but when we studied the period, we were actually able to observe that for ambient, that is for very atmospheric pressure, so very high pressure, the period is very small. And as we control the pressure smaller, we made the pressure smaller. As we made the pressure smaller, so at 10 millibar pressure, the period increases a little bit, and at very small pressure, that is at YChem 10⁻⁷ millibar pressures, the period is very high. So as the pressure decreases, the period increases. And this observation could be explained by the influence of pressure on molten liquid flow. So by relating the equations of temperature-dependent surface tension gradient on pressure P and the period of HSFS, we were ultimately able to derive an equation which stated that the period of the HSFS varies inversely to the square root of the pressure. And this observation concludes that the HSFS have a hydrodynamical origin rather than an oxidation-based origin. So we begin with an investigation to study the influence of oxidation on the formation of HSFS, and we found out that the oxidation or gaseous or other gaseous environment has very negligible role in the formation of HSFS, and ultimately we concluded from this observation that HSFS have a hydrodynamical origin, or they are most likely to be explained by molten liquid flow rather than oxidation-based modes. So the most important conclusions that we get from this work is that HSFS of sub 100 nanometer period and sub 20 nanometer amplitude are formed for all the experimental conditions. And then HSFS can be generated on tungsten surfaces without the presence of ambient air and native oxide layer. So that indicates the insignificance of oxygen for the formation of HSFS. And HSFS are formed in the presence of a reactive gas like nitrogen or a non-reactive gas like argon. And then the period of HSFS can be tuned by controlling the pressure. So it indicates a hydrodynamic origin of HSFS rather than an oxidation-based origin. And also this further provides a better understanding for the surface chemistry involved in during the formation of HSFS, and it will further help the scientists to control the application of laser modified surface. So these are the important conclusions that we got from this work. And thank you, Manutech, for giving me the opportunity to present my work, and thank you all for listening to my work. Thank you.